All right, so today we have Florent Baume tell us about 60 SCFTs, long quivers, and super strong chains. Take it away.
Okay, so first let me thank you for the kind invitation. And today I'll talk about, as you just said, 60 SCFTs, and after all, it's a Quiver meeting, so I'll talk about quivers. So it's a work in collaboration with people that at the time were at Penn. So Jonathan Heckman, who's still at Penn, and Craig Lowry, who now moved to Daisy. And it's based on two papers, one that came out a few months ago and one from already two years ago. So, I mean, considering who I'm talking to, I'm not sure how much I need to motivate why 60 SCFTs are interesting, but let me quickly go through it. 6 is the maximum number of dimensions hosting an SCFT. That's a theorem that has been known for almost 25 years now. And starting from 60 by compactification, you can reach a host of lower dimensional theory, the prime example being class S. And they are also interesting because they are isolated point in theory space. There is no marginal deformation for 60 SCFT. So they are inherently non-perturbative. There's no deformation from a Gaussian fixed point. So if you want to learn about QFT, well, this is a very good place to start, since they're absolutely non-perturbative. And a very nice thing about supersymmetry is that if you impose supersymmetry in addition to conformal symmetry, then you open the doors of geometric engineering, where you can reach all the at least known 60 SCFTs from string theory. In particular, here I'll discuss mostly F theory, and the constraints are so strong that just by looking at anomaly cancellation condition, you can enumerate all the possibilities, the possible geometries that leads to a 60 SCFT, which was done by Heckman, Morrison, and Vafa with the follow-up with Urdelius a few years ago. Now, via geometric engineering, you get access to many physical and protected quantity. By physical, I mean, I'm really talking about conformal data, so gauge invariant operators, like the central charges I get you can usually read from the geometry, the flavor currents. You can discuss the chiral ring, or if you don't have chirality, in 60 BPS multiplets. But everything is in somewhere or another encoded in the geometry. So if you look at the central charges, which are essentially the 2-point function, the coefficient of the 2-point functions of flavor or currents or the energy momentum tensor, you can relate those to the coefficient of the anomaly polynomial. And again, this is completely fixed by geometry, essentially some intersection numbers. But the question I want to tackle today is, what if you're not interested in protected quantity, but quantity who gets correction via interactions? So unfortunately, there are not much that is known about them for specific theories. One possibility is to go via the superconformal bootstrap. In lower than 6 dimension, it's a whole industry. There are far too many people who worked on it. But in 60, there are, as far as I'm aware, only 5 papers, 3 in 6 dimensions, and only 2, only for 1,0. One about the E string, and one I had with Craig for type D conformal matter. So the question is, what can you do? So one possibility is to look at some large charge expansion, which is what I'll do today. You can either do it via holography or via what I'll discuss today. So you consider an operator that has a very large R charge. I have an SU2R symmetry. So I take something that has a very large charge, essentially a field to some power. I'll be a lot more explicit later, but just to give the idea. And the question is, can I have a large expansion. So can I compute the anomalous dimension just as an expansion of a charge? This is actually something that's a very old idea that traces back to the beginning of AD-SCFT, and there has been some other recent development, well, semi-recent by now, development by Hellerman, Orlando, and Reifert. Okay, so the outline of the talk is the following. I'll quickly review how you get those 60 SCFT and how you can interpret them as quiver in some generalized sense, and then how you can, for some types of operator, relate them to speed chains. Essentially, those quiver can only be linear. You have a 1D system, and we will associate another 1D system, which is the string chain. And I'll show that this is actually integrable, and I'll discuss a few generalizations, then I'll conclude. Okay, so 60 SCFTs. So it's been known for, again, quite a while now, that you can obtain 62,0 theories. There is an AD classification, and the way you realize them by F theory is that you consider 2B on an orbifold of C2 with some AD finite group. And one of the features of 60 theories is that you have a tensor multiplets, which I can think of dual to 60 strings. And these 60 strings, I can obtain them by wrapping D3 branes on some surfaces. Here, for 2,0, this is the P1s are the resolutions of the singularity. And it turns out that the tension of these strings is just the volumes of those surfaces. But if I want a CFT, I need to not have any scale in my theory, so I better send all the volumes of the P1 to 0, and that's how they were done. So the F theory point of view of that is, well, the lift is very easy. I'm taking the same orbifold of C2, and I just take a trivial fibration. So it's just orbifold times T2, and the AD classification really appears because in all its glory, it's already what happens in 2B. I'm just setting some notation. It will be if I blow up the singularity, it will be a bunch of -2 curves that intersect in the pattern of a Dynkin diagram. So here, a linear Dynkin diagram type A, type D, and 3 exceptionals. Now, if I want to go to 1,0, well, I have two possibilities. Either I play with the intersection number. So here, these are -2 curves, but I just arrange them in such a way that they look like the pattern, the intersection pattern, and I get rid of the minus sign for clarity. But I can, instead of having a -2 curve, have something that has another self-intersection. For instance, if I just take a single -1 curve, I have the E string. But I can also play with the fiber. So if instead of having a trivial T2, I take something that's singular, what happens is that I can associate a gauge group with that. And this will generically break supersymmetry, and I can explore a new types of geometry that leads to 1,0. But the thing is that not all possibilities will work. In general, these guys will be very singular. So if I take an E6 algebra over a -2 curve, I need to blow up to resolve the singularities and get something that fits in the usual Kodara classification. And what I find is that I will get a more complicated pattern than what I started with, and possibly with some flavor symmetry. So here, the only thing I'm saying is that if I try to fiddle with either intersection number or the algebra associated with the fiber, I will have to blow up some things, some stuff, which from the 60 point of view means I'm moving on the tensor branch. And so by doing that, since I have anomaly cancellation constraints to satisfy, well, what Heckman, Morrison, Waffa, and Rodelius showed is that this is enough to classify all the possibilities. And it turns out that they take a very, very simple form in terms of building blocks that are called conformal matter. So if I just consider type A, well, I have the usual bifundamental hypermultiplets. So here I just denote it by a dot. It has two SUK flavors. But if I go to other ADE type, I will have some things that are more complicated. So if I consider something with an SO flavor group, I will have a -1 curve with some symplectic algebra over it. So it's a generalization of the bifundamental hyper with some new flavor group. And if I go to the exceptional group, then I get something far more complicated. Again, here I'm not expecting you to remember the exact pattern. It's just that I get something more complicated. But I always have an ADE flavor on each side. So I can just think of them as just a link with G times G flavor. But now if I have flavor, I can do what I always do in 4D. I can start gauging the flavor together to obtain something new. Now I'm in 6D, so it's slightly more complicated, because if I just introduce a vector multiplets to mediate the gauging, generically I will not cancel anomalies, and I need to cancel them via Green-Strauss term, which essentially just means that I need to insert new curves. So if I start with E6 conformal matter, I have these two patterns, and if I want to glue those two together, I just need to introduce a new curve with some intersection number and some algebra. But the point is that I can just glue two conformal matter to get a new one. But if I can do it once, I can do it ad nauseam. And what these people proved is that all 1,0, there's a missing equal sign, all 1,0 quivers take this pattern. It's a long spine of conformal matter with some decorations at the end. And the point is that this spine, it's really a linear spine. I cannot have something that goes in other directions. If I try to do that, I will introduce gauge anomalies, so that the theory will be sick. And as I said, when I do that, I'm usually on the tensor branch, so the volume of the curves is non-zero, and the CFT point is the point where I collapse all the curves to zero size. And the point is that if I give you a quiver, essentially fix everything. I can read off the geometry. Well, this is just a representation of the geometry, but I can also get the matter content, the flavor, and everything. Now, the simplest case is just the type A case, where, as I said before, conformal matter is just hypermultiplets. So I'm just gauging a bunch of hypermultiplets together. And from the M theory point of view, if you prefer that one, this is just M5 branes probing an orbifold singularity. And on the tensor branch, if I look at the perpendicular direction, I just have, I segment the line into different segments which fix the gauge couplings, and by going to the CFT points, I collapse them all in one point, which essentially he's collapsing all the curves to zero size here. Okay.
I have a question.
Yeah.
What are these phi's that you put?
So here, in the case of type A, this is just the hypermultiplets. So I have a doublet in the SU2 representation. I'll be more explicit in, I think, 2 slides.
So phi stands for a hypermultiplet, even though the typical notation is different.
Actually, this is maybe more what you'd prefer. So the hypermultiplet is just a doublet, so I can think of them as morphism going from one node to the other.
Okay.
Is that?
Yes.
Is that
fine? Okay. Yeah. X and Y are more conventional. Okay.
Yeah. So here, yeah, I should have left it as a without the phi's, but yeah, what I mean for type A is really I have morphism going from one node to an adjacent node. Yeah.
Okay. Thank you.
Yeah. So as a doublet of SU2, they have to be in the same gauge representation. So I have a Y dagger, but yeah, this is exactly what I was saying. Okay. Where was I? Yeah. So at least in the free field limits, I know it's a free field, so I know the conformal dimension of these guys. But generically, if I have a full quiver, then I have some gauge indices that I need to construct, and one possibility is to construct something that's gauge invariant by looking at the baryon. So I just chain all the hypers together. That gives me something that's gauge invariant and that transform in the bifundamental of the two groups of the two flavor.
And you know it's not appropriate to call them baryons, right?
It's I agree.
Okay.
This is essentially the only time I will say baryon. They look like some people are less confused if I call them baryon. I will just call them bifundamental operators that are just a chain of hypers.
Fine.
Here I'm using phi because I can either take a bunch of x's or I can do something more complicated. The point is that if I take them to be all x's, well, the hyper is half BPS, so I just have a bunch of half BPS objects. So I can also know the conformal dimension, just L times the conformal dimension of one hyper, so it's 2L. But now, if I start switching x's for Y daggers, it's no longer half BPS. So it will get an anomalous dimension. So the question is, can I find this anomalous dimension? Before doing that, I'll just mention a few observations. Is that the position into this bifundamental operator is fixed just by gauge invariance. Also, the quiver looks like a 1D object, so does the bifundamental. So I can see inserting y's as impurities into some operator, which means that I essentially have a one-to-one correspondence between these bifundamental operators and spin chains operator. If I define the BPS1 as saying that all spins are up, which is their highest weight of the SU2 representation, so plus one half. And then if I start switching x for y's, I just flip the signs. Now, what if most of the sites are spin up? then I'm in some kind of dilute gas approximation. So I better these states are almost half BPS, so there should be just a small deformation from the conformal dimension of the BPS operator. And in particular, what I'll show now is that this is fully calculable. Now, before doing that, via interaction, an impurity will be able to hop from one side to the other. And what I'm actually interested in, the quote-unquote true conformal operators, so the eigen operator of the dilatation operator, the dilatation generator. And this is very similar to what was done in the early 2000s with n equals 4. So instead of having a doublet of SU2, they had a spinor of the SU4 asymmetry. But in our case, we have bifundamentals instead of adjoint scalar. But again, it's very similar. We have this bifundamental BPS operator, and they just had trace of Z to some power. Here, the power is fixed because we have a quiver that has fixed length. But in their case, they found it was integrable, and in a very similar way, we'll find that this is also integrable. Okay, so there are some subtleties with the 6D computation. So let me first discuss what happens in 4D, which is just the reduction of this quiver on a T2. But there, at the level of the quiver, nothing changes. You just take it as an n equals 2 quiver. But now I have a conformal manifold. So the gauge coupling at each node I can play with. In particular, I can take them to be small. So I can use F theory. And the hopping of an impurity from one side to the other is mediated by F theory. So the goal is to find how the mixing works. You can start with just one impurity and see what happens there. What I'm interested in the conformal dimension, so it's I need to look at the 2-point functions. Now, I can do a perturbation around the BPS value, and if you do the full computation as you would do in an advanced QFT class, since there are composite operators, you'll find that the mixing matrix is given by this anomalous, this mixing matrix gamma tilde. It's just a prefactor that encodes the gauge coupling with some group theory factor and some other one numbers. But here I have only nearest neighbor interactions. So everything else is 0. So to find the eigen operators, I just need to diagonalize this matrix and, oops, let's see, slightly skewed, sorry. I see that the full anomalous dimension is just the conformal dimension of the BPS object plus some number that comes from diagonalizing the matrix times G square over L square, which means that even though I started with perturbation theory, so something that was a G that was very small, it's always suppressed by the length of the quiver. So as long...
What's G?
Sorry, come again?
What is G?
The coupling at each...
you're still
for each node.
Dimension.
Yeah, I'm still in 4 dimensions, yes.
I see, okay, thank you.
Yeah, a priori they can be different. I just, for simplicity, take them all to be
the same?
To be the same.
Okay.
But the point is that even though I started with perturbation theory, I can take them very large to the non-perturbative regime as long as the length of the quiver is also large. Now, if I start going, if I start considering more impurities, well, then I'm essentially playing the same game. I can encode everything into the dilatation operator, which just reshuffle the spins. And since it was nearest neighbor interactions here, oops, it's still nearest neighbor interactions here. And knowing that and the one impurity sector, you can write the full Hamiltonian, and you can write it in a compact way in terms of the R symmetry generators as ladder operator who just flip the spins. But this interaction Hamiltonian is nothing but the Hamiltonian of an XXX Heisenberg spin chain. So it's integrable, which means that if I give you a number of impurities, I can find the eigenoperators and their anomalous dimension very easily. So I have access to the full spectrum, at least at order 1 over L, and as long as I don't have too much impurities. But by too much impurities, I mean as long as this regime is valid. And as I was just mentioning, even though I started with very small G, as long as this ratio is small, the perturbation, the anomalous dimension will still be small, and I can still compute it.
Florent, may I ask
Yeah.
a question? So
Sure.
Here, what you are showing is that this particular set of operators lead to an integrable system. You are not saying that the 4D theory is integrable, right?
Yeah, I'm very good. So yeah, as I'm only talking about this type of operator, I can consider many other operators, but so for instance, I could take XY, that's a singlet, and take it to some large. Here, for that case, I have no statement at this point. And even though I don't think this will be integral, it's just that special subsector here. Now, okay, very good. Well, what happens now in 60? In 4D, everything was nice. I had access to a marginal deformation. So I could extrapolate. But now in 60, the Young-Mills coupling is that, well, first of all, it's dimension full, and it's proportional to it's given by the VEV of the scalar inside the tensor multiplets. So if I don't want any scale, I have to set that to 0, which means that I'm in the non-perturbative regime. But from holography, I have some hints that I can still do a large L expansion, because if the holographic dual is just ADS7 times S4 over ZK, and I can think of the quiver as just deconstructing a great arc going from the North Pole to the South Pole, which on the tensor branch I split into segments. Now, from the holographic point of view, the Young-Mills coupling will be the length to some power, but again, it will be dimension full. But I have still an effective coupling where I just take GE effective. I know that it will scale with the length of the quiver, so I can take that as at face value and think of this as a holographic regulator on the conformal side. which means I can essentially do the same kind of computation in terms of this effective coupling. The mixing will be exactly the same. The only difference is that now, before the scaling in 4D was completely arbitrary. Here, it's given. I know from holography what the scaling has to be. But I'm still in a good place, because this ratio here is still it's still a 1/L to some power expansion. It's just that that ratio is now fixed. But in the large L limit, I can do exactly what I was doing in 4D. Okay, so the upshot is that to a quiver of gluing conformal matter together, I can associate a spin chain, and the spin chain is integrable. And for each of the bifundamental operators I was considering, the BPS one and all the ones with impurities, they are now just a spin wave. So I just have impurities that travel the spin chain. Now, for the anomalous dimension, this will just be in correspondence to the energy of the eigenenergies of the spin wave. This has the solution to this problem has been known for quite a while again. It's given by the beta ansatz. So if I write the momenta of the impurities along the chain in terms of the velocities, well, I have the so-called XXX beta ansatz, which is given by this horrible equation here, which essentially tells me that the momenta on the left side, I have the condition of the momenta, and on the right-hand side, how they scatter with each other. But if I solve that equation, then I can directly find the energies. So in principle, I can find in the large quiver limits, I can find the anomalous dimension of any of the operator. In practice, it's much more difficult because solving the beta ansatz is a notoriously difficult problem, at least at a high number of impurities, but at least in principle, I'm in a good place. The only thing I need to think about is that in 6D, I have an extra condition, which is that I need to take that the sum of the momenta has to be 0. This can be understood in M theory. When I collapse all the M5 brane together, I cannot have momenta leaking at the edge. So I just need to take that the sum must be equal to 0. This has the benefit of avoiding some unitarity bound violations, because if you look at the representation theory, the conformal dimension must satisfy some inequality, and there is a gap between the BPS states and the long multiplets. And I only have this problem in 6D, but if I impose this momentum condition here, you can show that all the states who would have violated this inequality get decoupled. But that's just a small caveat for the 6D case. Now, until now, I only talked about hypermultiplets, so type A conformal matter. Can I say anything about the other types? Now, you can actually see from the geometry that the hypermultiplet has dimension 2. If you look at the hypersurface equation, all the variables must scale into some way. And what Jonathan showed, based on some IDs that were, I think, first used for n equals 2, if he showed that the holomorphic tree form associated with this hypersurface must scale in some way. And if you put everything together, you can see that the scaling of the variable x has to be 2, which is exactly the conformal dimension of a hyper. Now, you can do that for the other types of hypersurfaces for type DE. Essentially, the same argument still holds, and what you'll find is that instead of having hypermultiplets, that's a doublet of the in the doublet of the R symmetry, you have for type DE something we call the conformal matter operator, which transform into higher spin representations of the R symmetry. So for SU2, I have a Dinkin index 1, so the spin is 1/2. For type D, I have spin 1, and for exceptional, I have higher spins. So now instead of having a doublet, I have just some higher dimensional representation. But at the level of the spin chains, essentially nothing changes. Before, I constructed a BPS operator by taking the highest weight of the hyper, and then I didn't say it in those words, but what I was actually doing is acting with the ladder operators at a given site. But now for the other types, I can play essentially the same game. I take a BPS operator constructed out of the highest weights of these conformal operators, and I start acting with the ladder operators. The only difference is not, since they're in higher dimensional representations, I can act with the dilatation, the ladder operators, a number of more than once. So any operator. Sorry?
Can we go back to the ADE list of dimensions? So these are the numbers for omega. You get them from the equation for the ADE singularity.
This table, you mean?
Yeah.
Yeah, this gives you the. So I'm using. Later, I talk about the full superconformal groups. I'm talking about Dinkin labels. So I mean the mathematics convention. Yeah, so that's what you get for the representation of the R symmetry. And if you know a bit about the geometric realization in F theory, you can see that this is just if I go back. The nodes when I glue two conformal matters, I will have 2 for type A, 4 for type D, 6 for E6, 8 for E7, and 12 for E8. And this table is just sorry, it's just half of those numbers. So for E6, I had 6. So yeah, there is probably some representation theory that's at play here. I personally don't know exactly the reason, but that's what you get when you play the scaling game.
Okay, that's fine. Okay, thank you.
Problem? So yeah, instead of having a spin chain of normal spin, I just have a spin chain with higher spins. Now, as if this spin chain is integrable, we don't have a proof, but from the holographic point of view, there is really no difference between taking a ZK orbifold of S4 or some more complicated orbifold. So what we expect is that everything should go through, because essentially from the holographic point of view, I have fluctuation of this great arc. So I would also expect nearest neighbor interactions, and at least at the qualitative level, there's no real difference between having type A or type DE. So what we expect is that you'll get an integrable spin chain, but an XXX W/2 spin chain instead of 1/2 spin chain. So the only modification, yeah.
Go. Sorry.
So at the level,
sorry. Someone I thought was going to ask something. Julius, you were to ask something. I don't know who. Well, okay. If not, let me ask. Florent, the question is the following: when you mod by set K, right, on the S4, is the quiver you generate circular or linear? The quiver you are having in mind.
It's linear. It's linear.
Linear still. Okay. All right.
Yeah. At the picture, let's say, level. Yeah, I really have the exact same thing. I'm just the only thing I'm changing is the group of the gauge node. Okay. The conformal matter will change, but qualitatively it's still a link. It's just a different link.
Thank you.
Yeah. So again, we expect it to be integrable.
Yeah. So the picture. I think the thing which confused Carlos is the picture of the sphere that you had before. Can you go back to this picture?
This one, yeah.
This one. Yes. So it's not really the case like that, because all M5 branes are on top of each other, and the transfer space is what you get from taking R5 and divide by ZK, where the ZK acts on 4 out of 5 coordinates, right?
So yeah, holographically, well, are you okay with this picture for ZK?
Well, what would it be? I think the question of Carlos is what would the picture be for ADE?
Well, slightly on the tensor branch, I will still have the same picture. The output.
You're not distributing the single. You're not resolving the singularity, the ZK singularity. All points are on top of each other. There's no non-zero P1s, right?
Yeah. So I'm working. So I can always work on the tensor branch, right? Where the P1s have some volume. Before going back to the CFT point, and there.
Your idea 7 is assumed to take a collection of M5 branes, to put them on top of each other, and that they combined generate an ADS7 geometric dual. So why do you give them some distance? Those would be perturbations around ADS7. How do you motivate?
But they are separated on the. They are on top of each other. On the.
I don't see any other way for the holography. If you want to get ADS7, you need to take M5 branes, and you need to take them all on top of each other, and then in the near horizon geometry, they look like ADS7. This is equivalent to taking n equals 4 and saying that you are taking many free branes and you separate them. And it's not done like that. Carlos has more experience about it.
Well, you also have more experience than me. What am I missing? Let me just think.
Well, Carlos, is there any study of separated free brains?
No, sorry, I was not asking in detail the question that Ami wants to ask, but most for Florent. I was thinking more about these systems that Abruzzi, Fassi, Tomasiello, etc. Those systems I associate with 1,0 conformal field theories, right? They are systems that live in massive 2A. That's why I was asking what type of quiver you find in this case where you work in M theory. But okay, we can discuss this at the end of the thing because it goes for long.
Okay. Yeah. So. Yeah. Okay. Maybe let's discuss it again.
Well, maybe I can answer partially. So when you're pulling the M5 brains off, you're doing two things. One is you're sliding them slightly down the radial throat of the ADS7. So what we're doing is a calculation slightly away from the conformal fixed point, but where the gauge coupling is very large, and we have a canonical value of that being set by basically looking at the M2 brains stretched between the M5 brains. So the point, though, is that the quiver literally is deconstructing an arc between the North Pole and the South Pole of the S4. I don't think there's any doubt about that. So if you ask about the group action on the S4, there are two fixed points, one at the north, one at the south. And so then the picture that Florent is drawing is, if you like, a cartoon, but the idea is that each one of these little finite segments is associated with the 7D Yang mills, but it's being produced. There's also something going on in the ADS7 direction to slightly slide them away. So that's the picture we have in terms of the gravity dual.
Okay, thank you.
But as Florent has on the slide, right? G effective is very, very large. So so this is the point that usually we say it's hopeless to calculate anything because the gauge coupling is formally infinite at the fixed point. The point, though, is that because we know the scaling of the gauge coupling is only going as the smaller power of L, the 1/length expansion allows us to still get a perturbative expansion. Yeah, I think you're about to say that. Sorry.
Okay, maybe we can leave more holography for later, and Florent can continue with the spin chairs for now.
Okay. Yeah. So, okay, barring the discussion, I don't expect much of a difference. So I still expect integrability. I think it was proven by, well, again, early in the integrability discussions, if you say that the system is integrable and you give me a spin, then integrability, I can directly give you the Hamiltonian. And it's again the same, it's nearest neighbor, but now instead of having just a linear function of the nearest neighbor, I have some higher order correction to maintain integrability, which from what I've said before is not really something surprising because as you go from type A to D and E, the quiver on the tensor branch becomes more and more complicated. So it's not surprising that I should expect that the interaction also becomes more involved. But it would be interesting to see if we can find the exact same thing directly from the geometry. Okay. So now that I've argued that I have an integrable SU2 spin chain, can I generalize that to something more complicated? Well, the simplest case is just instead of having a linear quiver, I can gauge the two flavors to get something circular. Now this is no longer in 60 a CFT. This is what's known a little string theory, but this is something you can realize in F theory. But at the level of the spin chain and the nearest neighbor interactions, there's basically no difference. The the operator I need to consider is slightly different because I need to have something gauged variance, so I have to take the trace. But for each link, I still have this nearest neighbor function that I have. So the only difference is really with boundary conditions. So instead of having an open spin chain in the case of the 6D quiver, I have to take a closed integrable spin chain for little string theory. Now, this is really the easiest thing you can do, but instead of the SU2 doublet of the hyper, well, they are just parts of a larger superconformal multiplets of the superconformal group. So instead of having just two scalars, I have fermions, and I can take as many derivatives as I want. But I still have the spin chain picture. I still can take the BPS operator. It was BPS before, it still is now. But I can add by using the generator of the superconformal group to get some new kinds of impurities, of inserting fermions, for instance. So in the last paper, that's what we did. So the simplest example of different impurities is just to take what's called the non-compact SL2 sector, where my generators are just the dilatation operator, the special conformal transformation, and some combination between the Lorentz and dilatation operators. So now you can show that these three operators satisfy some SL2 relation, but I can again play the same game. If I act with the dilatation, the translation operator, I just take covariant derivative of X, and the scalars are conformal primaries, so they annihilate also the BPS state. Now, the thing is that by proving integrability for the doublet of the R symmetry, we essentially did all the work. So it's nearest neighbor interaction, so I can just focus on two sites and focus on the SL2 eigenstates. So at one impurity, I have two choices. Either I take a total derivative of the two fields, but I know it's anomalous dimension because it's a total derivative, so it's just a shift by one. But I have another eigenstate, which is this one, but via conformal symmetry, I can just write it as the supercharges in some combination acting on this thing. But this thing is just an SU2 state. It's just spin up, spin down, minus spin down, spin up. So it's the spin zero representation of SU2. But I also know it's an SU2 state. So I also know its eigenvalue. And you can show that while it worked for one impurity, it will work for many impurities as well. You will always find either it's a superprimary or it's a superconformal descendant of something that has less impurities. So essentially, I also get something that's integrable in that case, and it just follows from integrability of the SU2 sector. So I did most of the work we already did. And in fact, not only I can do it for derivatives, I can do it for any of the other impurities. So adding fermions or some other things. Again, you will find that you play the same game. Either it's a superprimary or it's a descendant of something with less impurity. So by recursion, you can just you can prove integrability. And the upshot is that the only thing you need to compute the anomalous dimensions is a set of simple roots, because you have to find a basis of the generator and the highest weight vector of the conformal operator. So two possible choices for 4D and 6D are these ones. So everything is encoded into the Dynkin diagram with some special choice of roots. And here I chose something that has the SU2 sector as a simple root. And they have the bonus that the highest weight vector is just either zeros or the value of the highest weight state of the conformal operator. Now, there's something that I was not aware before, is that there might be different Dynkin diagram for a super Lie algebra. So here I gave two Dynkin diagram of the 60 superconformal group, but they are topologically different. So if I want to consider any operator, I will just act with the ladder of operator associated with the simple roots. But now it's exactly what I did for the SU2. I just now have more freedom. I can act at a given site with a given generator. But depending on the choice I did, this will be more complicated. Here, this one has the SL2 sector in it, but here I have the SU2R sector, but it's not explicit. I do not see explicitly the SL2 sector. So if I want derivatives, which is just acting with the translation operator, I need to work a lot more. So what I call the highly excited state is relative to the Dynkin diagram I choose. So it was called by Bizert the beauty and the beast, because in that one, I have a bunch of zeros in the highest weight diagram, so it makes the computation simpler. And in the other one, it is not as simple, so it's more involved. So this one is the beauty, and this one is the beast. Now, once I've chosen that, then I fixed everything. Since it's integrable, there is a beta associated to it. It's just more complicated. I have impurities for each root, and I have impurities for each velocities for each impurity. So it's just a horrible mess of coupled equations. But at least in principle, the only thing I need is the highest weight vector and the Dynkin diagram, which appears here with the kata. But once I find that, I can take it on a computer, wait a long time, and I can in principle find all the anomalous dimensions. Okay, so I'm almost exactly on time. So what kind of other generalization we are thinking about? So if you take conformal matter, you can start deforming the quiver at the edge, which I told you that the 60 quiver is essentially conformal matter with some modification at the edge. One possibility is to take Higgs flows of conformal matter, and this is done by giving a nilpotent wave to the flavor. So I can obtain slightly more involved quiver with some decorations at the end. And the question we are thinking about right now is, do you still have integrability in that case? So is it just a change in the boundary condition? It seems plausible. Or do you have to take some other kind of spin chain? Or does integrability even hold in that case? The other kind of thing is, as was mentioned before, I've only taken a special BPS operator. What if I take instead of something else here? This operator is holomorphic, so it has some degree of protection from supersymmetry. So do I also have integrability in that case? Now, for integrable systems, you usually have some pp waves limits in ADS. Do you also, what kind of pp wave strings can you have in our case? And also, does integrability hold if you go to higher? So that's the kind of things we're thinking right now. So just to conclude and summarize, every 60 SCFT, you can write it as a general quiver. You can write, oh, I see that here I use the term variant. You can have some bifundamental operator that you can think of as spin chain by implementing impurities to some ground state, and then you get the anomalous dimension from the beta ansatz in some large L limit. Okay, so thank you for your attention.
All right, let's thank Florent. Do we have questions or more questions? Now everyone is shy.
Florent, can I ask you something? So
Sure.
people are not shy. So in this comment where you talk about PP wave strings, what are you having in mind? I understand you have an operator, you can associate an integrable system with it.
Yep.
So in the PP waves, there was also, as you described, right, a long operator that its fluctuations you associate with the dynamics of the strings on the plane wave background. So here, are you thinking something along those lines, or?
Yeah, exactly. So there should be some like fast moving string description of that. What is
okay.
What is the description of that?
Moving? Okay, how is that string moving is the thing that is more difficult to say, right?
Yeah, exactly. Yeah.
Okay. All right. Thank you very much.
Any more questions? Okay, if not, I would say let's thank Florent again. No, Avi, you have?
Yeah, I wanted to ask, what is the set of operators which are which can be treated using the methods that you're using? So how far do you go from the holomorphic sector?
For starting, are you talking about starting with this kind of PPS operator? Or
yeah, so when you have a moduli space, and on this moduli space there is a collection of holomorphic functions which will be associated with
right.
And actually for the quiver that you took, the moduli space is quite elaborate.
Oh, certainly.
It's a very difficult moduli space. And so what you did was to take the approach of focusing on a single holomorphic function, and then doing some perturbations on top of that.
Precisely.
So
yeah,
go ahead.
So we did it for one kind of deformation, so one kind of BPS operator. But as you say, there are many more. I think this is half BPS as well. There are other operators, so we could, in principle, we could also play the exact same game for all the rest of the BPS ring. It's just at this point, it's just more. We find it works with that one. Can we now explore the others?
Okay, so but let's just focus on the left guy with the X's. So on top of that, you build insertions of what you call Y dagger, right?
Yeah. Yes. But these will not be holomorphic anymore. They are not protected.
Yes, so you have a ground state which is holomorphic, and then on top of that you have excitations which are not holomorphic, right?
Yes. Yeah.
So now, so I guess you could take all possible excitations by inserting Y dagger at a collection of places. So that's one family of operators.
Sure.
And that's where you stop for the case of.
So at this point, yeah, that's where it's.
Yeah. And then you're saying you could take other holomorphic operators, like
other holomorphic operators and play the exact same game. The question is. Okay. Yeah, the question is, do I still have integrability in that case? That's not guaranteed, right? There are examples in N equals 2 where you have a sector that's integrable, but the whole theory is not.
I see. Okay, and now comes another question on, there are the two barons, right? Because every SUN has its own baryon and anti-baryon operators that you take by taking the determinant. These are holomorphic functions. So you could take a collection of x's, take the determinant, and you can take collection of y's, take the determinant again. Now,
so here this is the same answer. It is another ground state for a spin chain. Then the question is, can I play the same game?
I see. And it's not clear, you don't know whether it's integrable or not. Is that
at this point, no.
I see. Okay.
But that's something Berenstein considered for N equals 4 Yang-Mills, doing these kind of giant graviton as the ground state, and then the excitations around that. More for N equals 4 Yang-Mills, though, not for this case.
And was this conclusive? Whether
that I don't know, but he at least could say that there was a similar, set of small excitations around this holomorphic operator. So I think the general philosophy is similar. You say there's a holomorphic ground state, perturb in some non-holomorphic way, but keep it small, and then there you can probably say much more.
Well, it's in N equals 4, so I assume the answer was yes, it's integrable. It's maybe not a closed sector. Maybe it mixes with other operators that I don't know.
Yeah.
I see.
But yeah, but presumably one could play same game in 6D.
Okay.
More questions?
Well, one natural question is, how much does it take to put those extra bound conditions, those nilpotent orbits, at the two endpoints? And is there control over there that you have still integrability?
So here, yeah, I don't really have an answer for nilpotent orbits deformation. At the beginning, I had assumed that it would be very easy. It would just be boundary conditions, but so for instance, for type A, you have a ramp where you start from SUK, and then you go from SUK plus 1, SUK plus 2 to some, to the SUN you are considering. And the fact that you have a ramp means that you screw up completely the matrix here. So I couldn't, I don't know if you, in that case, you have some control over the mixing, but to say whether it's integrable or not, I couldn't find the answer, at least at this stage.
Can you still assume it's a nearest neighbor interaction? Or you have terms which are non-neighbor?
So as far as I'm aware, yes, yeah.
But it will be very different matrix.
Yeah, the form of the matrix is the same, but the numerology is different.
I see.
Yeah, I was really hoping that there was some nilpotent orbits invariant, and this will just change the boundary condition, and I could go home. Unfortunately, it wasn't as easy.
I see. I suppose this you could play this game already in 4 dimensions, no?
Right. Yeah.
And no existing work of this.
Not that I'm aware of. No.
Okay.
If there are some work, I'd be very happy to know about them.
Okay. Carlos did some work on this.
Right. Do we have more questions for Florent? Because maybe we can thank him again now and move on to the informal part.
Thank you.